Welcome to week 11, the problem of the week, shake and bake, coupled oscillations. We're going to look at the asymmetric case. So if you remember in lab, we had the situation with two masses attached to three springs, and we had the situation where the two masses were the same, and we had the situation where the two masses were different. We're going to focus here on the case where the two masses are different, and just go carefully through how you solve this problem. The forces stay the same. Doesn't matter for the forces what the masses are. And when you're working out these forces, you just have to be really careful about sorting out the signs. So for example, if I want to look at the force from the spring on the left on the mass 1, when x1 is positive, I'm going to be pulling that mass to the right, and that spring is going to want to pull it back toward the left. Pulling it back toward the left means it's getting pulled in a negative direction, so that force is minus kx1. When I look at the force on the right, if the x1 is positive, it's going to want to push it back once again from the middle spring, the k prime. So there'll be a minus x1, but also the total compression of that spring is determined by the x2 as well. And so if the x2 increases when the x1 increases, there'll be no net force from that spring k prime. So that's how we get a k prime x2 minus x1. And then working in exactly the same way, you'll get the similar formula for the force on mass 2. Now what changes is the Newton equation of motion, because I have m1 x1 double dot is equal to the force on 1, and m2 x2 double dot is equal to the force on 2. What we're going to do is we're going to divide each of those equations by the masses, and then look at them as a set of coupled equations after we substitute in this ansatz, which assumes an oscillatory solution. So we're going to say x1 of t is x10 e to the I omega t, x2 of t is x20 e to the I omega t. And I should make a comment here. What we really mean is we mean the real part of that. So x10 and x20 can be complex vectors, and then we're going to be taking the real part at the end to give us what the real displacements x1 and x2 are. This is a very common thing. You've probably seen it before. When doing it this way just makes a lot of the algebra much easier, and so that's why it's often common to do it this way. So what we find is our matrix becomes minus omega squared plus k prime over m1, minus k prime over m1, minus k prime over m2, minus omega squared plus k prime over m2. That thing multiplied by x10, x20, that whole thing has to equal 0. The only way for this thing to have a non-trivial solution that's equal to 0 is if the determinant of the matrix is 0. And that's going to then give us the equation that we need to solve in order to find the frequencies for these oscillatory solutions. Now I do want to point out, if you look carefully at this matrix, it is not a symmetric matrix. So all of those theorems that we have about the eigenvalues always being real and so forth, they may not hold for this particular matrix. Okay, so let's take a look at what that determinant is. I'm going to get an omega to the fourth term. I'm going to get a minus omega squared times the sum of the k plus k prime 1 over m1 plus 1 over m2, and then for the constant term I'll get the product of the k plus k prime over m1 m2, k plus k prime squared over m1 m2, minus the k prime squared over m1 m2, and of course there's going to be a simplification in that final term, but we can immediately solve this because it's a quadratic formula in omega squared. So omega squared is equal to k plus k prime times m1 plus m2 over 2 m1 m2, plus or minus the square root of that thing squared, k plus k prime squared, m1 plus m2 squared over 4 m1 squared m2 squared, minus k squared plus 2kk prime over m1 m2. And that's actually the solution. I have to take the square root of the whole thing to get the final frequencies, but that is the solution. And I have to hope that what is going to happen is those frequencies are always, the squared frequencies are always bigger than 0. And you can see by looking at the square root that that's going to actually be the case. Now, if I took the situation where m1 was equal to m2, then you can see m1 plus m2 is equal to 2m. And that'll cancel a factor of 2m in the denominator for the first term. So I'll just get k plus k prime over m. And that'll be plus or minus, it'll be a k plus k prime squared over m squared. but that's going to be minus k squared plus 2kk prime over m squared. And everything is going to cancel except for the k prime squared over m squared is going to be left. I can take the square root of that. It's going to become k prime over m. So I will get k plus k prime over m plus or minus k prime over m. That's exactly what we had before when we solved the symmetric case. So this gives the right results when m1 equals m2 is equal to m. But it works in a little bit better if we massage the formulas a little bit, and then it takes a form that's perhaps a little bit easier to follow. So what we're going to be having in our case is all the springs are the same. So k is equal to k prime. And we're going to choose the first mass to be some factor times the second mass that we'll call lambda. And so what we find is our matrix equation takes the form that's given for you here. I don't have to read it out for you, but you get a 1 over lambda m for each m1, and you get a 1 over m for each m2, and the k's are all the same. And then when we look at the solution, we can write it in this form. K over m times 1 plus lambda over lambda plus or minus k over m times 1 minus lambda plus lambda squared divided by lambda squared. Now the case lambda equals 1 is the symmetric case. Let's just take a look at what we get in that case. 1 plus lambda over lambda, that'll equal 2. And then I'll get a plus or minus k over m times 1 minus lambda plus lambda squared. That's a 1 divided by lambda squared. That's a 1. And so the square root of 1 is a 1, and so I will get 2k over m plus or minus k over m. Well, that's going to give me k over m and 3k over m, and that's exactly what we had before for the different frequencies. So it works perfectly in that case. But now what we can do is we can take a look at what happens if lambda gets really large. So if lambda gets really large in the square root term, because I have a lambda squared divided by a lambda squared, that square root term is going to approach 1. And if I look at the first term, because I have a lambda over lambda, that term is going to approach 1. It's going to look like k over m plus or minus k over m. Now, it's not going to exactly be k over m plus or minus k over m, but what it tells us is one of the frequencies is going to get very small, and the other one is going to be on the order of 2k over m. So some number on the order 1 times the square root of k over m for the frequency itself. Now, let's try and see if we can understand why in the world is one of these frequencies getting very, very small. Well, if one of these masses is really big, so if m1 is much bigger than m2, then we have a situation where m1 just isn't going to move very much because it's incredibly massive. And so it's going to act primarily, it's going to look like m2 is completely separated. It's kind of like k prime is attached to a wall where m1 is, because m1 isn't moving very much. And so the m2 spring is going to act pretty much independent. That's going to give us the faster frequency, the one that goes like the square root of 2k over m. And the m1 is going to give us a really low frequency because it's going to just look like some kind of square root of k over m, but where the m is huge because it's a very massive mass in that case, in which case we'll get this very low frequency because the mass is so large. And so that explains why these numerical results will go the way that they go. The other thing to keep in mind is, well, what happens to the eigenvectors? Well, we didn't actually plug in the numbers and work out what the eigenvectors are. It's a little bit of a pain to do that. But what we do know is that there's going to be one eigenvector where the x1 and x2 are both positive. And if the masses are close to each other, they're going to be close to being the same value, but not exactly the same. And there'll be a situation where the x1 and the x2 are opposite each other, but once again, they won't be exactly the same. One will be slightly larger than the other in order to give the eigenmode. And this is actually something you can test a little bit if you want with the apparatus to see if you can guess at what that eigenmode might be and see whether or not you can excite something that comes pretty close to just exciting a single eigenmode. You can tell that it is properly excited because you'll just see that same oscillatory motion going over and over. You won't see any kind of beat phenomena where it switches between the two modes or anything like that. Okay, that's all that I have today.